Can you see it there?
Yes. Mm-hmm.
Yes, so
I
that
see
is
the first slide. Thank you. Colleagues?
It's okay.
Mm-hmm. All can see and listen.
So thank you, and I'm going to present on the topic of spatial data and technologies for geomonitoring of mining environment and competing land use. The case studies in Kenya. Taveta is a big region of 17,000 square kilometers. And you can see our students at Taveta University visiting one of the mines there. And mostly quarrying, mining and quarrying activities, mainly surface mining. But we need geomonitoring and spatial data to monitor the environment and aid government in policy and planning for sustainable mining practices. So we'll go through the background, just to know something about Kenya and Taita Taveta. And our main problem is in governance. Government needs data and needs models to advise on strategy. Again, we need to ensure sustainability in the mining sector, so we need to marry our research with sustainability. Then we'll see some of the findings and implications for further research and policy advice. So for those who have not come to Africa, you can see Africa is also rich in minerals, with South Africa on top, but also Congo, Morocco, Guinea, and Namibia. And Kenya is somewhere here. So in Kenya, we are a leading producer of soda ash and fluorite. In Kenya, we have 13 large-scale mining companies, and a good number of them, almost 50%, foreign-owned. In Taita Taveta, which is the study area here, you can see it is near Tanzania, southern part of Kenya. We mainly have artisanal and small-scale miners. We call them Zurura here in Kenya, but in South Africa, they are called Zamazama. In this county, we have rich minerals, mainly precious stones. You can see tourmaline, savorite, right, which is green garnet, and various varieties of tourmaline and other precious stones. But we also have manganese and iron in this county. Most of the activities here are surface mining activities, as you can see. Not far from Taita Taveta, we have a large-scale mining project for titanium. And the company doing this is also a foreign company from Australia called Base Titanium. This iron ore site is a large-scale mining project in Taita Taveta County, which is the study area. Kenya still has a young and growing mining sector. The major contribution to our GDP is from agriculture. But you see, mining is still below 1%. And we have in our development vision the target of improving the contribution to be at least 10% by the year 2030. That is why we need research collaboration to improve the mining sector. And it is this one which is represented here, very low relative to the other sectors in terms of contribution to the GDP. Why do we need geomonitoring or remote sensing technologies in Kenya? We do need because all these issues are key in our mining sector. The same in Africa, land rights, safety in mining, how to share benefits with communities, and this is of rights for children and gender issues, especially women. We need accurate data on location and on socioeconomic activities mapped in a way that policymakers can understand and can address the conflicts with visual intelligence. That is why we need geomonitoring and spatial data. The main challenge, if you ask me, in Africa or Kenya's mining sector is about governance. So we need regulation, community engagement, and all these need data, especially digital data and technology, so that we can improve output from mining activities. If we continue with artisanal mining with low technology adoption, then we cannot produce much. We also need to tie mining activities to the Sustainable Development Goals. You can see number 7, 11, 13, 14, and 15 are key Sustainable Development Goals which we need to consider in our research, and they are all interconnected. That is why this study did not just conduct data analysis, but also developed a model for policy and planning using system dynamics. From literature review, we have these main sectors that are researched on for mining studies, and the bigger balls are where we have most studies if you conduct literature. But from my literature review, I realized that there are very few studies that are integrating environmental and management sciences with economic and social sciences, systems analysis, and geospatial analysis. So my research area is at the intersection of all these spheres. And that is why it used systems thinking in order to look at the big picture. If you look at the study area, you will notice that we have mining activities in the north-south direction. This is where our university is located, Taveta University. The government has built a center here, gemology, to train miners in gem cutting, because we have many gemstones in this area, and we are surrounded by counties such as Kwale all the way towards Nairobi. Nairobi is in this direction. Agriculture is also a main economic activity in the area, and that is why from this mapping you can see the classification of the area into different agricultural zones. The green areas most suitable to agriculture, the same as this dotted area near our university. And we just discovered some manganese around this area last year. So this one shows you that mining activities are competing with agricultural activities and conservation. Conservation because in this county, we have 60% covered by a game park for animals. So we need to manage all these competing activities in a way that we can ensure sustainability and human rights, protect human rights. The game park I'm talking about is here. It has been mapped here, Tsavo National Park. So you can see it is covering 60% of the county, of the 17,000 square kilometers. And the mines are here. Some of the mines are in the game park. The rivers are also spread all over, and most of the people get their water directly from the rivers. So we also need to protect the rivers from pollution due to mining activities. So this places the study squarely within the realm of environmental management, integrated environmental management. The methodology used for the study is systems approach. So the scale is not on a project level scale, but an entire community scale. And that is why systems thinking approach was found suitable. Traditionally, most of the studies in this sector have been using the traditional linear approach, where you focus on one sector, looking at mining alone. But here I'm looking at mining together with population growth, other land use activities such as agriculture, forestry, wildlife conservation, and protection of water resources. Again, in this study, we don't have definite boundaries. Rather, we look at the entire region as consisting of interconnected sectors. Seeking solutions, having a predictive model instead of reacting to outcomes, and it is also long-term. The model is suitable for long-term planning, not short-term planning. This is the geospatial workflow, how spatial data is getting extracted to feed the model. So we have a combination of ground surveys and remote sensing. The thicker line means where more data is coming from. So from remote sensing, most of the data is unstructured or semi-structured and medium to high resolution. From ground surveys, I use GPS surveys to establish control points in the area so that when conducting the spatial analysis, I could check the accuracy and notice if the images were correctly georeferenced. So again, before I get data into the system dynamics model, I have to ensure that the data are structured into data layers. I use a standard reference system and geodetic datum, correct coordinate system for the area and map projection for calculating areas. In Africa, we also have an initiative that is providing ARD, that is analysis ready data from satellite imagery such as Digital App Africa. And these are good prospects for geomonitoring in Kenya and Africa. So in the GIS-based multi-criteria analysis, I'm combining spatial criteria with factual criteria. Factual criteria include policy provisions in the mining sector, stakeholder views, and spatial criteria are extracted from spatial data, georeference data, so that we can calculate areas, we can calculate distances from hotspots, mining hotspots to water resources or agricultural areas. So in summary, all these three stages have been followed sequentially until I arrived at the parameters for the decision support model. So if you look at what other researchers have done, when talking of sustainability, they have been considering mainly three pillars: economic, environmental, and social. Some researchers have gone further, like Q et al., in the mining sector to include the local community and the mine owner. In my case, I've improved on this using a conceptual modeling framework, which you can see here. So looking at the study area, I identified all the key sectors in the study area that need to be looked at in an integrated manner. So in the county of 17,000 square kilometers, mining activities interact with people, population growth, and as population grows, land use changes, urbanization, and agricultural practices. But you also need to look at the agricultural sector. How is agricultural land use claiming space in the area? As we said before, most of this area is under a national park. So we also need to ensure biodiversity conservation. We also need to conserve the forests, because forest cover is a key factor in environmental management. The water resources, it is a semi-arid area, so we need to conserve our water resources, the surface water resources, against pollution, and ensure that the buffer zones that are designated to be free of human interference are preserved. And you can only do that effectively through remote sensing. So from all these sectors, if you look at the interactions in two ways, it is a complex nexus with conflicts and competition on limited space. So from the systems approach, we are combining all these criteria and having a facility for simulating into the future what could be the outcomes. And these are of important implications for policy and management options in the mining sector, because the mining sector is not alone. It is interacting with the other sectors. And any decision made must include what is happening in the other sectors as well over the years. So I've used system dynamics application software called Stellar. Using Stellar, I've come up with stock and flow diagrams for all the 6 sectors: water, the national park, the forest cover, agricultural areas, mining activities, and other processes like reclamation. And when we do exploration, if we get new mining blocks, they are part of the model that, as you run the model, show how the mining area is changing over the years. And we have a rather complex sub-model here, which is on population growth over the years and change in urban area and urban population density. These are important parameters for development planning in the county. And down here is now a summary to see the mining area as a percentage of the land area that is being used for other activities such as agriculture, forest, and water resources. So in this part of the model, as you run the model, you get the ratios land area balance, that is the total county area, the protected area, where protected area are these green areas. We need to protect them. The agricultural land, forest cover, the national park, and the surface water area. So all the area calculated is under protected area, summed up under protected areas. Then by subtracting protected area from county area, you get the land area balance. Then by getting the gross mining area divided by land area balance, you get the mining area percentage of this land area balance. So these are important ratios that policymakers would need to decide on how mining activities should be managed and the speed at which we should be conducting post-mining, closure, and reclamation for proper environmental management. the software as a model layer, and you can equations layer. You can see under the equations layer, we mainly have differential equations because it's a dynamic model. So for a county population, for example, from 1979, where I start the simulation from, you get the time difference and you multiply by the number of years and you get new values. And as I use the software, I found out that the normal numerical integration using Euler's integration was sufficient to give us accurate figures, which I compared with historical figures and found that the difference was within less than 10%, which is good for modeling. And in terms of satellite imagery that covers this area, you can see Landsat 8, the image covering part of this area, not the whole of it. And Rapid Eye, which has a very good temporal resolution of daily coverage. But most of the Rapid Eye images in this area just covering the north-south direction. And most of them interfered with by a lot of cloud cover. The best image source I got is Sentinel. And you see Sentinel-2, the one in green, is covering the whole area that I wanted to study. The red is Sentinel-1, but for this study, Sentinel-2 is sufficient to help in discriminating land use and showing how mining activities are competing with other activities and any clearance, land clearance that is caused by surface mining activities. So Sentinel was the choice source of imagery for this study area. In Kenya, we are developing an online mining cadastral portal to manage licensing for mining areas and to manage the mining blocks better. So this is an example from the ministry in charge of mining in Kenya. And as we conduct more studies in geomonitoring and spatial data technologies, we contribute towards improving such a framework for managing the mining sector in Kenya. You can see we are using, they are using WGS84 as the system for mapping and searching coordinates within this area. Some of the results you can see, there is PlanetScope, which is also providing good spatial resolution of 3 meters. The images I got for this area are mainly covering the central parts. And what you can see from PlanetScope imagery for these areas, this Wanjala mine is the large-scale iron mining area. And this Gregory, this is a smaller mining area for gemstones. And the message here is that whenever you see active mine, like Gregory is an active mining site, you see the land is bare because of clearance, and is showing how actively mining is affecting the environment around it. We also have some lime works here. This is for mining limestone, and it is surface mining activity. You can see the clearance that is going on around that area. This mine, at the time of mapping last year in 2018, it was closed because of conflicts between the community and the mine owner. There's conflict in terms of land rights, ownership rights between the communities and the mining owner. There is boundary dispute, and this one needs geospatial technology so that there can be clear demarcation of the boundaries for resolving the disputes. If you look at this area, you can see from the legend that there are settlements and farming activities. This is because it has been an inactive mine for a long time. So from PlanetScope, again, we can see how the area is changing over the time and the kind of activities going on. These ones in blue are springs. There are freshwater springs in this area, and these are still having good land cover in terms of vegetation and well preserved. This is Sentinel for the whole area. From the Sentinel imagery at 10-meter spatial resolution, Sentinel-2 image, you can see it is covering the whole of this area. You can also see the iron ore site I was talking of. And even from Sentinel imagery, you can still see that this inactive mine has a lot of developments, human activities going on around it, and some vegetation or crop farming. This is mainly cropland. Coming up, when you look at this area with so many mines, you can see most of the mines in the north-south direction are competing with human activities, development, and even plantation and cultivation by the people around there. The areas without mines, like this area we call Taita Hills, mainly still having forest. And this is a good analysis to show how mining activities are competing with land use and land cover. If you can remember, our university, which I showed you, is located around here. And even where the university is, there are many active mining activities going around there. And it is a good opportunity for our university through research to contribute to sustainable mining practices through training and using geomonitoring to show how mining and environment are being, environmental management activities are progressing. So in terms of the population sector, all the way from 1979 and projecting to the year 2029, I took a 50-year period. This is how population growth has been going on in the area. You can see there has been change in the population growth rate from 3.45% to 1.76% per year. But from 2009, again, the population has been growing at a high rate, 3%. That is significant. From spatial analysis, is showing where we have high concentrations of mining activities, around 800 hectares, these areas, from GS analysis. And they are not far from the game park, which is here. In terms of water resource management, this river is the main river that is passing in the most populated town in that area called Voi town, Voi. When I conducted a water quality test, in total dissolved solids, you can see quite high numbers, total dissolved solids in terms of milligrams per liter, and increasing downstream because of activities. You see human activities are very close to the river, like brick making, grazing, logging of trees, and sand harvesting. And such kind of spatial analysis is important for environmental agency in designing interventions to manage the environment and conserve the river environments. In the model, I have 53 mines, and 53% of them from this GS analysis located within 4 kilometers from the main water points, which again is a key policy message that we need to protect the water resources which are close to the mining areas through proper mining practices. The area is divided into these administrative locations. You can see these 7 administrative locations. And from the model, by using distance as a parameter and as a proxy measure of the risk the water resources in these areas are facing because of mining activities, we can come up with a summary which has been useful to the community and policymakers to see which areas have higher risk of degradation from mining activities, where the waters have higher risk of degradation from mining activities. And we can see from here, it means these 3 areas are facing the highest risk. And so something should be done, and stakeholders should be involved in ensuring that sustainable mining practices are going on, and that we plant trees and we minimize destructive activities that are conducted without any measures to stop erosion or extensive land clearance. From the simulations, forest cover is a key parameter in environmental management. So this one is already showing from the simulations how forest cover can change over the years, and urban area over the years. And another important outcome here, these 3 lines are showing the annual water demand over the years, simulated annual water demand from 1979 to 2029, agricultural area using the data on agricultural area change, data from the Ministry of Agriculture in the country, and important also the county population growth as simulated. And the numbers, as I said before, were different from the actual census by less than 10%. The simulated figure for 2019 was 355,798, but when the government released the census results, it was 340,671, which is also a good simulation because it is only 4.4% difference. This model is also helping the county to budget for annual water demand, 26 million cubic meters by 2019 and 31 million cubic meters by 2029. This is using the index of water requirement per person multiplied by the population that is projected in the county by 2029. So it is a model that can be used to simulate different scenarios. Here you can see the green line and the blue line in the simulation showing us the difference when we have the active mining area over the years. And when I run the model, I get this green line as simulated active mining area. So it means if we can get mining areas from different years from satellite imagery, we can still simulate into the future and predict the trend. And you can see the difference between the blue line and the green line is small. So this is also showing the predictive accuracy of the model and the sensitivity to changes over time. So that is what these 2 lines are here for. This line is the mining area balance over the years. And this is simulated reclamation how much area is being reclaimed after mining. And it shows very well that if you increase the area you are reclaiming over the years, then you also find that the mining area percentage goes down, and that is expected. So the model is giving us a predictive validity that you expect, and you can now use it with more data from geomonitoring, with more data from GS analysis. You can calibrate the model and get better results over the year. So it is a tool that is flexible, and with more data, it can be used for more applications, especially policy monitoring and planning. So in summary, this model integrates spatial data and the technology which is useful here, mainly satellite imagery, satellite remote sensing, that is GNSS, optical surveys a bit, and dynamic modeling. Main application, compliance monitoring, ensuring transparency in the mining sector, and including the public participation. With this kind of model, we can have better classification of the images using machine learning algorithms. And DEA is Digital Earth Africa, which is providing analysis-ready data from satellite imagery and can help to improve this study. We have also been talking of mini satellites, but even better unmanned aerial systems, including drones, would be very useful to improve the resolution of this study and better metrics for simulation. So in conclusion, it is a generic model that is adaptable and is flexible enough for simulations and systems analysis. It helps the people and communities and policymakers to get a shared visual understanding of what is going on in the mining environment. We can see large-scale impacts, inform policy and strategic planning, and can also monitor the mining environment, any illegal activities in a visual and transparent manner. And as we look into the future, more and more of such models will be required because the issues are complex, they are conflicting and competing. Because of that, sector-based approach is limited. We need an integrated approach, which I've shared through this example of geomonitoring and system dynamics. So way forward for policy perspectives in Kenya would say we need better regulations, which will even help us to use more of drones. Drones are not yet licensed in Kenya. We don't have a law that is permitting the use of drones in Kenya. But if policymakers can come up with regulations that allow the use of drones, it can be better for more detailed geomonitoring in mining areas and compliance monitoring for that matter. And with increasing digitalization, we can have more analysis-ready data and get more data from the public for better simulations and a better planned mining environment. Thank you for listening, and I'll be happy to get your comments and questions.
Mm-hmm. Thank you very much for interesting and comprehensive report. Dear colleagues, we are waiting your question.
Nashon, I have a question.
Yes.
With what program did you simulate the situation with mining areas?
Okay. I used a program called Stella.
Okay.
Stella, S-T-E-L-L-A. So it is the oldest system dynamics application software, which was developed way back in 1985.
Okay.
That's the best interface. Did you get my answer?
Yes, okay. Thank you.
Yes, yes.
Other question, please.
Yes. Can you hear me? I have a question about a drone and how government right now provides that regulation about you shouldn't use a drone, or you have a free regulation and you can use a drone for every day.
Thank you. In our neighboring countries, Rwanda and Tanzania, the governments have already allowed the use of drones. For example, in Rwanda, drones are used for medical service deliveries. In Kenya, why our government is still saying we should not use drones is because of security, because Kenya in this region is strategic, and it is a target of many terrorists. So that is why the government has delayed so much, saying there are security issues that need to be looked into so that they can come up with a better regulation and strategy to avoid the use of drones for other purposes, I mean national security. But it is already being discussed in Parliament, and hopefully by the end of this year, we'll have come up with firm regulations that will allow the use of drones, but in a way that wrong use for terrorism and spying can be prevented in time effectively.
Understood. Thank you for your answer.
Other questions, colleagues? Okay, as I understand, there are no other questions. I think it depends on so comprehensive and
May I ask a question?
Yes, of course.
Yeah,
Yes.
But may I also use the screen demonstration if the organizer would allow me to demonstrate the screen, but there is no permission for me. You know, I use Grace satellites. Катя, может быть, включишь мне разрешение?
Of course. Just a second.
I use Grace satellites which can detect the mass changes in the basins of different rivers all over the world. And I just, while you were making a talk, I was interested in your region and tried to show, to get the plot for Tana River. Is Tana River far from the place of your study?
Yes, it is far from this place, about 500 kilometers.
Кать, у меня не включается демонстрация.
Okay, but I didn't see. Oh, just a second.
That was the only river I found in their database.
Okay, I'll try it. I tried to add administration role. Just a second, Leonid, sorry.
Yes. So I'm sorry for the, I would like to show you this plot, but it would be possible.
I'll try. I'll try again, just a second.
I wonder if, I guess it's not very big river, but
a big river.
It's not a big river, but if I start, it will stop the demonstration. And I got such a plot. So I wonder if you can make any comments on it, because I wonder why in recent years the variations became much more, I would say, prominent. Can you see the plot?
Yeah, yes, I can see the plot. And the line is mass change.
Yeah, it's an equivalent water thickness. The satellite measures the margin, and over the basin of Tana River, there are such variations. Maybe river is too small for such satellites, but I wonder, could it be that in recent epochs, variations of the water in the region becomes more, what's to say, variable, I would say.
Yeah, it becomes variable, especially in the month of April. In the month of April, we have a lot of floods in Kenya and much rainfall. So if you check the month of April, you may see there's a big change, positive change in the mass of water.
Thank you. We can find maybe some common points for future collaboration using different kinds of data. Thanks.
Welcome.
Thank you very much, Leonid.
My pleasure.
Sorry for problem with connection and the change in role. Okay, are there any question, colleagues?
Yeah, good day. Do you hear me? Ekaterina, do you hear me?
Yes, yes.
Yes.
Now, yes, very good.
Yeah, I have one question. Because I know that in some, for example, Russian mining and in Europe and in States, you usually making monitoring using satellite radar data, and the accuracy of radar data, for example, for some mining activities, is more accuracy, yes? And the question to the presenter: do you use the radar data in your on your case studies?
No, for this case study, I did not use radar data. I was mainly interested in calculating large areas of change in land cover and land use. And multispectral imagery was sufficient for that. But if we are to study smaller areas and go into changes such as land subsidence, I think radar data will be very useful. For example, what we are getting through Sentinel-1 and other studies that require interferometry. So radar data would be a good addition for further studies, especially when we want to go deeper into what is happening around the mining sites themselves. But for the entire area and studying changes in land use, I found multispectral imagery sufficient for the purpose of the study.
Okay, thank you for your answer. And do you see, I just a few months ago read some articles about Sentinel-1, yes, and they also use it for mining, yeah. I know that RadarSat images it's too expensive, but Sentinel-1 is for free, so you can easily use it. And in one software named Snap, yes, there is some manuals for interferometry processing, so you can easily use it for just to count the difference in, for example, some ground measurements. It is very easy.
Yeah, the ground movements, it is very good here. Thank you.
Thank you for question and comments. Are there any questions? Okay, as I understand, that's it. Okay, Nashon, thank you very much for interesting report, data, and presentation. Later, I'll add the material to our news feeds of our group. And I believe and I hope that we continue our joint research and we will make a new publishing, especially with comments from Leonid and Andrei, and maybe the other colleagues, I don't know. Okay, and thank you very much, Nashon. Thank you, colleagues, for company and discussion. And I think now we stop. Have a good day, and thank you very much. Bye-bye.
Bye-bye.
Bye.
Bye.